a fundamental problem we have in physics today. And that is that our two most fundamental theories, the General Theory of Relativity and quantum mechanics, do not work together. And when there are problems that are needed to work together and to be together, they, due to their very nature, cannot. And this is a problem that puzzles physicists, because how can we have our two most fundamental things that explain everything not working together? So in this video we will explain why this division occurs and what are the proposed theories for a unification to happen, and if a theory of everything will ever be reality. To start this journey, we'll start with the General Theory of Relativity, and that is that gravity, the General Theory of Relativity, says that gravity is a consequence, an effect of the very geometry of space-time. And Einstein was telling us that space-time tells matter how to move, and matter tells space-time how to curve. And this idea is understood by the fact that space-time is not something rigid, something that cannot be bent, but that space-time is actually very flexible. It's to think in a simple way what space-time is. Think of a cloth extended to the point that when you put something heavy in it, it makes a dent. So gravity is that. The Earth follows the curvature, the dent that the sun leaves on space-time. The moon follows the dent or the curvature that Earth makes on space-time. And this is really the essence of the General Theory of Relativity. And an important concept we need to understand, and that will be used later in this video, is the speed of light, c. The speed of light is an invariable, which the speed of light is the same in all circumstances, and that nothing can go faster than the speed of light. And this idea will be used later in our video, and will be used to explain why gravity and quantum mechanics are not united. So now that we see this beautiful idea, the General Theory of Relativity by Einstein, we will now see what a standard model is, and to understand why it is now being incorporated, we will now see what the standard model is. So to understand the standard model, we will use a conceptual map made by Professor Marco Antonio Moreira from the University of Rio Grande do Sul in Brazil. So the standard model identifies two basic particles, the leptons, which are the electron, the muon, the tau, the neutrino of the electron, the neutrino of the muon, and the neutrino of the tau. It also identifies 18 different quarks. And the hadrons, which are actually made as antiquarks. These are the elemental particles of matter. These are our most fundamental particles that we know of. And these particles interact with the fundamental forces. The electromagnetic force interacts by the photons. The strong nuclear force interacts by the gluons. The weak nuclear force interacts with the particles W and C, and the gravitational field interacts with the very speculated gravitons. These are the particles of force. So the latest discovery of the standard model is the discovery of the Higgs field. So the Higgs field is what gives particles its masses, and why we see that some particles have no mass and others have. So the particles receive a mass, but the way they interact with the Higgs field, the more they interact, the more mass they have, and the less they interact, the less mass they have. So now that we've understood the standard model, I will invite you now so that we may think and reflect why we haven't found a way to incorporate gravity in the standard model. Dimension analysis by done by Professor Cesar Gomez, we will use a universal constant, which is the constant of gravity. We use the dimensions of this constant, which is these. Of course, we will write this equation as follows. And v time squared mass. Of course, we know these are dimensions of velocity, so it will give us mass c squared. So when we solve for L, we see that we are at a gravitational longitude, which would be g and c squared. Now, to make our lives easier, we will see that c is equal to 1. Thus, our gravitational longitude will be equal to g times m. We will do the same thing for quantum mechanics using the principle of action. What is action? Action will be denoted by the word s. This is the dimensions of action, and action is what tells us what really happens or what may happen. Why something follows a straight path? That is because it is the minimum action required. So if we know, we change this equation, we arrive at a new way to see what action is, and that is that action is energy times time. So we organize again this equation. We'll do this, and we will write a new way to see what action is. That is momentum times longitude. And this is a new way to see what action is. So now the question is, what is the minimum action required? And for that we use another universal constant, and that is Planck's constant. We will use Planck's constant by this h of the cross, which is h of the cross means Planck's constant divided by 2 pi. And the dimensions of this constant are m, l, c. And if we do the same as we did here, we arrive at our quantum longitude will be equal to h between m. So now we have two constants, and we will see how they both, we will compare the two. Compare the two longitudes. In a classic model, we would have this a normal building, this is a gravitational building, and this is a quantum building. Now we are remembered that we have disconnected all of the other forces except for gravity. So this is an electron, gravitational electron, quantum electron. So now our question is, what is the minimum quantums of action required? That will be denoted by the letter m, and that will be equal to the dimensions of action, which are these, and Planck's constant. This is telling us that n will be equal to 1. So if n is equal to 1, we see that a normal building, n will be far greater than 1. In a gravitational building, n will be greater than 1. In a quantum building, n will be equal to 1. But in the quantum scale, these two are not possible due to Planck's length, because this is telling us, these two, that n is less than 1, and that, due to Planck's length, is not possible. Here, n will be equal to 1, so this is possible. But our dilemma lies here. Gravitational field behaves like a quantum field, and due to Planck's length, it is allowed, but we cannot see it. And that's by the fact that quantum come in packages. So when we do this number at 1, the number will be duplicated. And if we do the same to the gravitational number, it will be insignificant. Thus, we will not see it. And what Cesar Gomez is proposing is that we modify Planck's theory, so that we done by taking the minimum action required and making it n times m. So, if you allow me, Mr. Planck, this could be one of the proposed theories that will unite gravity into the standard model. Thank you for watching.